as the matrix element of the row when all the elements have the same value, and we consider another type of the. And the only things remain is that I explain how to find the average of the quantity like Hamilton energies. So some properties of that. So rho mn is 1 over n, as you see, a m chi, a m chi star. And they are function of the time. The properties of this, of rho. First is that rho is symmetric matrix. The rho is symmetric matrix, actually not symmetric, it's Hermitian, but many reasons it will be symmetric. So let me to see that what does it mean. 1 over n sigma k 1 to n a m chi star. I want to see that, can I write that like what is the condition to have the same expression like that? The condition is that n chi should be a n chi star. So what does it mean? What is the a n chi? A n chi was phi n psi chi. If you want, we can write in this notation of the derived. And that was you can set the star inside. So the eigenfunctions must be real functions. In this case, the matrix will be symmetric. For example, we can consider the phi n like this is. Those are the wave function for the particle in the one-dimensional box. Quantum box. Yes?
That's square 2 over y or 2 over a?
Yes, 2 radical a. Long time I didn't use this. Can check it that, but let me see phi n squared ax 0 to a will be integral sinus squared. Sinus is 1 minus cosinus a double and ax on over to ax. So will be yes, will be pi over 2. So radical 2 over a. So for example, for these functions and for a wide class of the models, the rho is considered as a symmetric matrix. More generally, it is better to say that this is a Hermitian matrix actually. But we call it symmetric. The other condition is that the rho square is rho. This is very strange that rho square is rho. If you multiply this matrix to itself, you give 1. I want to show that how is possible this? So is symmetric and it satisfies a question like rho squared approach. What is the rho square? This equation should be for any element like Mn. What is the rho square Mn? It's rho Mn. From the elementary matrix algebra, you know that if you want to find the Mn component of the multiply of the two matrix A, B, Mn will be sigma chi N chi beta. It's written in any textbook of the, you know that from the past. So here we have the same that, so will be sigma chi rho M chi rho chi N. And now what I will do is that I replace the expression for the each row here. I cannot use the same car because car one time use it here, so I use L as an index for the element of the ensemble. P, for example, I use it. I write this 1 over n squared this. I think we have to use more information here to derive these expressions. So, for example, you needed to know that what will be that. Because the k is set here, so k is not the index. K is not the index. No, k is just the index for the element. So it's not the index which we use it for the ensemble. So this is just the k is just the k, not going to the end. So this is the index which refer to the total number of the ensemble elements. Numbers of ensemble elements. this will be the LL. This is a, you can use the definition of AK and substitute that here, and you can show that it will be reduced to the delta economical actually. You remember this equation sigma A and correct star over the top and so that equation will be similar to that. So, but no, it will be n multiplied with this. I will explain you later because I want to very fast from the property just and go to define the average. I will expand that and you will see how later. So because it needed, I substitute the A, L, P here, intervals, and I use the completeness conditions. Anyway, I will have just this, and L and P are similar, so you will have just one. And this is the row. This is the row if this condition is satisfied. So the important things, and by this equation, actually almost the chapter finished. So the next chapter, the next section after that next lecture will be to give you some real example like the harmonic oscillator, like particle in the box, and find for them what is the row. So you understand that the row here is a matrix, and it has the one differential equations. If you just replace it, the Dirac brackets by the Poisson brackets, or vice versa, and of course you consider IH bar, you can go from the Liouville theorem to the quantum version of Liouville theorem and that's all. And you learn that there is a two property for the row. Row is symmetry and row is square is row. So I want now to averaging a quantum ensemble. For the averaging, and you know in statistical physics, you know average, everything is finished. So average of any operator I want to define, so it will be, you see this is the difference of, one of the difference of in the statistical averaging and the normal averaging, I will tell you. Averaging in the statistical physics is double averaging. You have a quantum state, you have a wave function for each element of your ensemble. For example, you have a 1 million hydrogen atom, one of them is in the orbital S, one is in orbital P, one is orbital D, and 100 of them is sitting orbital S again. So at each time you know what is the wave function of each element of your ensemble, no? Because I told you, I gave you this information, I told you one of the atoms, for example, as an element, is in orbital P. So you can read the wave function for orbital P. If you know. So, from quantum mechanics, you can take the expectation value of any operator. No? For example, expectation of the operator of momentum at one of the elements. I mean, if you measure the momentum of the spatial element in your ensemble, how much will be the momentum? This is that. But you have several elements, so you don't have the one element, one one atom. You have a huge number of the atom. You collect all as the answer. So you needed to again make another average. This is arithmetic average, and this is a quantum expectation value. Huh? This is very important. So quantum statistics is like a double averaging. One time you needed to find the expectation value of the operator. Not the expectation value, this is the exact expectation value. And second time you need to take the average of them. For example, in the room you have a different people, so they are almost the same, but each one can have a different blood. Yes? You can have a different blood group. Huh? You have a different people. So each one has a wave function. So the wave function for them is the blood group of these elements. Blood group. So this is its psi. Psi of this is psi A plus. See, this is a similar actually, but just the difference is that in quantum mechanics you have more than these few numbers of quantum. So, and somebody asks you what is the how much you expect that here in the system you can find a particle, how much you can expect that to find some element of the ensemble which they have the same blood group. You don't know that what's the operator to find the same blood groups or something like that. But I mean, you needed first to check each element and see that this element has the blood group which you are looking for, that or not. If you are looking for the B plus, for example, first it's like algorithm. First you check, put this in the algorithm. If this is a B plus, you keep it that. Huh? Go to the next one and remove that because it's not B plus. Go to the bus, remove that and keep it, or remove or keep it home. And finally you will have some different people with the same blood. And now you can make an average and tell me that how many of the particles in the whole system have this B plus. This was the easiest example I can find. So just replace each person by the hydrogen atom, for example, and give more than one possibility. That there is a one blood group for everybody, but for hydrogen atom you can have a different energy level. So each energy level can work like one blood group for them. So you know the situation will be very complicated because this situation you have just one level, one energy level. But there you will have a more. So you understand that you needed one quantum averaging inside each system and make it the arithmetic averaging after that, or normal averaging. This is the normal average, 1/n sigma, the grade of the system. This is a normal part, and that's the quantum part. It's related to information inside the system. And that's all. So now you can just replace psi car. What was the psi car? You remember the psi car was expanded in terms of the psi car, you write sigma and Cn, if you remember. Yes? You can replace the psi car here and just make it a little bit more simplified, these expressions. I want to conserve the time, just conserving the time. So just replace it, that's here. Psi ka a star, so will be sigma. I cannot use ka again here, unfortunately.